designed, developed, built, and tested by Boeing in El Segundo, California. So this is TDRS-K. This is the first one. TDRS-L will launch from, all three of them will launch from Cape. But TDRS-L will launch essentially a year from now, mid-January of next year. And TDRS-M is planned for launch no earlier than December of 2015. So, in addition to the satellites, what was also part of the program for the continuation of the space network, the TDRS Space Network, which is a constellation of TDRS satellites that have been up in orbit for over 20 years. There had to be modifications and enhancements on ground and software enhancements at White Sands Complex, just outside Las Cruces, New Mexico. As you can probably understand, and I just mentioned, the TDRS constellation has been up in orbit providing data, video, and services for over 20 years. And so, as technology improves or enhances over a period of time, there has to be corrections or enhancements to the ground hardware and software, which was part of this program or contract. So some of that was part of the program cost of the 3 spacecraft, and then we have to find the launch vehicle for each satellite to be able to deliver the satellites to a separation orbit, and then the spacecraft itself will provide its own propulsion system that provides it or boosts the geosynchronous. So I think to date, the contract value the government has with Boeing is on the order of, for the ground and the 3 spacecraft, this ULA provides the Atlas launch vehicles.
But that's included in the total.
If you want the total program cost, which includes the launch vehicle, the ground, and the 3 satellites, it's a little over. It's like 1.1, maybe 1.2 billion.
Which should we use? 1.1. Okay, 1.1. Is there a way to break out a satellite roughly, or should we just divide by 3 and say heck with it?
I think if you divide by 3, it's close. It's close enough. I mean, so let me explain a little bit about that, because there is a difference between the cost between the cost of the first satellite and the cost of the follow-on, and because of that, is that you learn a lot of engineering design and parts obsolescence on the first one, and you take those lessons learned and apply them to L and M. So roughly it could be divided by 3. But the thing about the TDRS-K KLM satellites is they all have the same design. They all were procured at the same point in time, except for M, which was contractually exercised about a year ago. The reason we did that is the government doesn't want to have to pay for a non-recurring effort more than once, because that's where all your costs are. So the last series of satellites that were launched for NASA to the space network or to the constellation was TDRS-HIJ, which Boeing Hughes was the contractor. It was back in 99, 2000, 2001. So that's when they were launched, but the design of those satellites were back in the mid-90s. Okay, the design, the parts procurement, all the subsystems were procured and designed back in the mid-90s. Well, fast forward now, what, 10 years, 12 years later? Well, now we have cell phones, now we have these laptops that are all mobile, everything is electronic. So there's been a lot of technology advancement over the last 10 years. So it's really not it's not even close to being a build-to-print satellite from HIJ from 10 years ago because of technology and advancement. So a lot of the parts, materials that the government procured through Boeing to build the satellites are obsolete now. So there was some obsolescence, that we had to design around or design for, parts obsolescence down to, when I mean parts, I mean like, ICE, integrated circuits and capacitors and resistors. They've advanced in technology, so the design of that into new units or components have changed. So that's the non-recurring that we had to pay for.
But let me ask, I mean, let me make sure I'm not misunderstanding, because it still seems $350 million for this satellite and a rocket seems like a great deal. It seems like it's lower than it should be. We were just talking about how the Landsat's like $850 million for one satellite and 2 sensors and a rocket. No, I mean, I'm not asking to compare apples and oranges. This seems like it just seemed lower than I was expecting.
Well, okay. You really can't take 3 and divide by 3. Because again, the non-recurring design effort was on K. So I would say K plus the launch vehicle for K and the launch vehicle, and the ground mods, which wasn't a big factor, it wasn't a big cost. But K and the first launch vehicle, I would say, is probably on the order of $500 million. Again, it's because of the obsolescence from the last one to this one, and the changes in design, and even not only that, but the people that were around at Boeing and Goddard back in the early 90s, some of them have retired, have moved on. Boeing's engineers and technicians, some of those people have advanced to upper management, so there's knowledge that has to be relearned, from the engineering level, and so that's the part that costs the money.
So, in a nutshell, how differential compared to what's up there now?
Visually, it's essentially the same. And I mean, if you had TDRS, one of the HIJ series here, right next to K, it would be almost like that. What I mean by that is that single access antennas, those great big antennas that are up top that are kind of folded or rolled in.
No memory,
well, there is a memory, and we know how long they can stay furled until that memory is gone. So no, there's a memory. But that's.
But you guys opted for that versus the mechanically deployable antenna, I guess.
This is the same design and same material that's flown on HIJ. Yes, and it's Boeing proprietary.
And I'm sorry, I didn't mean to interrupt you.
So let me get back to the question, but that's a good question. Essentially, they would be identical, just visually. Same antennas, the same space-to-ground link antenna, which is the smaller one that's kind of encapsulated in there. So what's different in terms of visual is, for example, the solar arrays, the solar rings. You can see that they're stowed, they deploy. And so one of the technology advancements over the last 10 or 15 years is the efficiency of solar cells. And so, though this bird requires more power, because the electronics and the performance of the data services has gone up. Meaning usually the bandwidth, kind of like your Wi-Fi, internet, everybody wants to visit. So there's more people on the TDRS-K communication services. The power goes up, but we're flying smaller solar arrays or less populated solar cells on the panel because the technology is moved. So the deployed length of the solar array is the same, but the population of the cells on the panel are less because of technology advancement. So that's a visual change. And visually, HIJ series and K is the same, but in terms of bandwidth capability, in terms of how much data can take this satellite versus KLM versus HIJ is probably, well, we'll see when we get on the work. We've designed to use a factor of 4 or 5, higher bandwidth. Again, demands have increased. Design capability has gotten better. Quantum circuitry is more robust. We understand the vacuum of space and radiation a lot more now than we did 15 years ago. So that requires that you put the users between now. User satellites that NASA has, the space station or Hubble. All the Hubble images come through TDRS. All those beautiful pictures that we see on the national news and national press that you guys put out. those all come from TDRS. All the video that we see from the space station and the astronauts, shuttle was flying, and all the video that we saw, all comes from TDRS. And then all the NASA low Earth orbiting satellites, other than Hubble, which are on those posters that were in the constellation. You turn one of those over and it has a list of all the satellites. So all that data comes through the TDRS constellation. And so more satellites are put up in orbit, the user load goes up, so the requirement for the bandwidth and data service. Rarely. So essentially, no.
Oh yeah, it's in manual. Oh, I'm so hot.
So you essentially have 3 orbital zones, if you will, so that's why you have 4 spacecraft.
No.
Too simplistic.
No, well, it's a good question. No, with the 9 that we have up there, they're strategically located, you know, at geosynchronous altitude around the Earth to be able to provide communications 24 hours a day, 7 days a week, 365 days a year, continuous data communications to the group that I just mentioned. So if one of the legacy spacecraft fail in the next year or two, and we have to decommission it, what I mean by decommission is moving it out of geosynchronous altitude by about 500 kilometers, kind of like really valuable beachfront property. You know, it's geosynchronous altitude, so we have to move it out of the way. So it may be moved into a replacement slot from one of those decommissioned satellites, but they're all strategically located around the Earth to provide 24/7.
Let me ask a newspaper story. So I'm looking for a quote that I'm fishing here.
Okay.
And I understand the answer before I ask the question.
Okay.
It's in your pamphlets and we've all covered this.
Okay.
But when you tell somebody it's a communication satellite, they picture what sends down CBS or ESPN or whatever. What makes this different from a garden variety communication satellite that private companies launch all the time?
Well, sure, and yeah, in layman terms, I understand. In English. I can't speak for, and I don't want to speak for it, but I can't because I'm not knowledgeable. You know, but I can't speak for, I cannot speak for, you know, the Defense Department and their comm satellites. The comm satellites that the NASA has are TDRS, and a lot of the satellites, you know, send their data through this. So the only, my knowledge of other comm satellites or commercial, like you said, could be, for example, DirecTV. XM satellite, you know, any transponders for cable TV. Boeing provides, you know, those services, or build those satellites for like DirecTV. So that's all, you know, I guess you could say entertainment in terms of, you know, television. What's different here is that it's all for science and for human exploration. Again, station, shuttle, those flying, Hubble, with all the images, you know, all the scientific images and scientific data, in the future JWST. So it's all science-related communication information versus more of a commercial, which is, you know, satellite radio, cable TV.
So it's not so much this is more sophisticated per se, it's just a different mission.
Yeah, it's different requirements, different, you know, different data services. Ours is more of science and voice and data from that standpoint versus radio and television. But it's essentially the same type of technology. It's just different with that, and it's implemented differently. So from settings for